Yes, hello students. In this brief lecture, I will discuss the basic equations and characteristics of DC motors. So, all this you have studied in your previous course of machine also, but there is a brief review of this so that you are familiar with these equations. So, the basic equation is the first equation is the EMF equation, and that is some constant as phi into omega m p phi nz upon 60a that we have studied earlier, but here the constant I have taken as ke phi omega m, phi the flux in Weber, and omega m is the speed in radians per second. The second equation is the torque equation. This also you are familiar with. K into phi times Ia. Phi is flux and Ia is the current in ampere. So torque is in Newton meter. So this is second equation, and the third equation which relates E and V, the supply voltage V, and the back EMF or induced EMF in the armature E. So the back EMF will always be equal to V minus the drop in the armature circuit resistance. This resistance Ra includes the resistance of armature winding, resistance of brushes, resistance of series winding if it is there in the case of series motor. So all the resistance which is there in the circuit of armature is known as armature circuit resistance. So E will be equal to voltage, supply voltage minus the drop in the armature circuit resistance. And usually this drop is very small, and you can say that the back EMF is always equal to the supply voltage. So E is approximately equal to supply voltage. So this you must remember. It is very important that whatever the situation, E will be close to the supply voltage V. Now if we take from equation 1 and 3, you just equate it. V K phi omega m equal to V minus Ra Ia, and multiply the equation, you will get omega m equal to V upon K phi minus Ra upon K phi into Ia. So this is equation number 4. So this relates speed with the armature current Ia, and if you replace Ia in terms of T from equation number 2, you will get this equation omega m equal to V upon K phi minus Ra upon K phi square into torque T. So this is equation number 5. So these are basic equations. Now let us see what happens if the motor is a shunt motor and what happens when the motor is a series motor. For shunt motor or separately sided motor, the flux is constant. So the term Ke phi, K is a constant, phi is also constant. So this is a constant. Let us give a name equal to constant K. So equation 4 and 5 becomes omega m V upon K minus Ra upon K into Ia, and this equation 5 will be omega m equal to V upon K minus Ra upon K square into torque T. Equation 6 and 7. So using these equations you can plot a speed versus current or speed versus torque characteristics. Both equations are of the form y equal to mx plus c, a straight line equation, where this is the c component, that is the constant component, and this is the slope. So the slope is negative, so the characteristic will be drooping in nature. So if you see here, I have plotted the speed versus current and speed versus torque. In both cases the equations are identical, only the constants are changed. So whether you plot speed versus torque or speed versus current, the curve will be identical. So I have shown here that it is a drooping characteristic. This point is the no load speed. When the current is 0, then this is a speed. So this is actually equal to V upon K. This point here will be simply V upon K. That is the no load speed of the motor. So as the motor is loaded, the current increases, the torque increases, the speed will drop, And as I have shown here that this is the 1 per unit point, that is the rated speed, and at no load the speed is equal to 1.05 per unit, that is 5% more than the rated speed. Usually this is the case, the speed drop is about 5% as the motor is loaded from no load to full load, and the rated speed is that speed at which the motor will run when it draws the rated current. It is supplying the rated torque. At that condition, the speed is known as the rated speed. So this I have shown as per unit speed, 1 per unit speed, and as the motor is unloaded, speed will increase, and at no load condition it will be about 5% higher than the rated speed of the motor. So the speed is drooping in nature, and this drop in speed is basically because of the resistance Ra. Had the resistance been 0, in that case the speed would be V upon K. It remains constant throughout. This means that larger is the resistance in the armature circuit, more will be the drop in the speed as the motor is loaded. So it is tried that the Ra should be, the resistance of armature circuit should be kept as low as possible, so that the motor behaves like a constant speed motor. So this is a characteristic of a separately excited or shunt DC motor where the flux is constant. In series motor, the flux produced by the motor is proportional to armature current, because field winding is placed in series with the armature. So the flux there will be proportional to armature current. So I have taken it equal to Kf into Ia. So if you put in place of phi, you put Kf into Ia, equation 2 will become equal to T equal to Ke Kf Ia square. So the torque depends on square of the current, whereas in the case of shunt motor, the torque will be proportional to current. And the speed equations in terms of current and torque can also be written from these equations. So they are shown here: V upon Ke Kf Ia minus Ra upon Ke Kf, equation 10, and speed omega m equal to V upon square root of Ke Kf into 1 upon square root of torque minus Ra upon Ke Kf. So the equation number 11. So these equations can also be drawn here, and you can see that the characteristic, because the characteristic now depends on Ia also. So this is inversely proportional to Ia. So the speed decreases as the current increases. So the characteristic is highly drooping, and you can say that when the load is 0, so the torque will be the speed will be very high. So speed tends to infinity at low load condition. So this is a very dangerous situation. So DC motor is never used in those situations where the motor load can drop such that the speed becomes very high. Usually it is used only in those situations where the load is expected to fall to only that value such that its speed is double the rated speed, because operating the motor above that speed will be dangerous for the motor. So now you can see one more thing you can see here, why the speed drops more in case of series motor. You can view it in this way also. You see question number 1. In the case of shunt motor, flux is constant. So as the motor is loaded, flux remains constant, back EMF remains constant. So this speed remains constant, almost constant. The drop is only because of armature circuit resistance. But in the case of series motor, as the motor is loaded, this flux phi increases. When this flux phi increases, and E has to remain close to supply voltage. So this means that E is constant, but the flux phi is increasing. So this will cause the speed of the motor to drop. So the motor speed drops more rapidly in the case of series motor as compared to shunt and separately excited DC motor. So this is the way you can explain the characteristic of a series motor. Now here one more thing you can notice that after this point I have drawn a straight line here. So this means that when the load is more than the full load, after that saturation occurs and the flux does not increase beyond certain value. So after that flux remains constant. So after saturation has occurred, the flux will remain constant, and then when the flux is constant, the characteristic will be like that of a shunt motor. So it will be straight line after that. So this straight line shows that the motor has saturated. The flux is not increasing anymore with the increase in the armature current. One more thing you can see in the case of shunt motor, I have drawn a straight line here, but one factor also helps in getting good speed regulation, and that is the armature reaction. Because of armature reaction, as you know, as the motor is loaded, the flux is decreasing slightly. So the drop in speed because of armature circuit resistance is partially compensated and the speed becomes slightly higher. So the characteristic will bend slightly upward because of armature reaction like this. So this will be the characteristic of the shunt and separately excited DC motor. In the case of compound motor, that is cumulatively compounded motor, the characteristic is in between these two characteristics. So the no load speed is not dangerously high. It is limited by the flux produced by the shunt field winding, and it is more drooping as compared to shunt and separately excited DC motor. So this means that characteristic of compound motor is in between the shunt and series motor. Now the second characteristic that I want to discuss here is the current versus torque characteristics. Usually in machine paper you have studied torque versus current characteristic, but here I have drawn current versus torque because this torque depends on load torque. So load torque is independent variable and torque has to depend on that load torque. So torque is equal to load torque. So this is also independent variable, and current will depend on the torque on the motor. So current is dependent variable, so it is taken on y-axis, and the independent variable torque, which is always equal to load torque, is taken on the x-axis. Now as you can see from equation number 2, that torque is proportional to Ia in the case of shunt motor, phi is constant, so the curve will be linear, Ia is proportional to torque. Whereas in the case of series motor, you can see that torque is equal to Ke Kf Ia square. So Ia is proportional to square root of the torque tau. So the two characteristics are shown here like this. So you can say that the current versus torque characteristics of shunt motor will be a straight line, whereas this will be of parabolic shape like this. What is significance of this characteristic? Let us try to understand it. In the case of shunt motor, as the load torque is doubled, the current will also be doubled. So suppose this is the full load point at particular point. This is the current drawn by the motor, and this is the torque. If the torque is doubled or torque is made 4 times, then this current will become 4 times in the case of shunt motor, because torque is current is proportional to torque. So if the torque is made 4 times the rated torque, the current will become 4 times the rated current. Whereas in the case of series motor, if torque is made 4 times the full load torque, the current will be only 2 times the full load torque. So there is less increase in the armature current on overload condition in the case of series motor as compared to that in the shunt motor. So in the situation where the motor is subjected to frequent overloads, then the use of series motor is recommended, because in that case the current will not shoot up beyond the safe limit. As you know, the maximum current allowed in DC motors is about twice the full load current. So this means that if you are using a shunt motor, you cannot go beyond double the full load torque. But if you are using series motor, you can go to up to 4 times the full load torque. So you can safely overload the motor without affecting the performance of the machine, or without sacrificing the life of the machine, without damaging the machine. So this is recommended that when overload is there, frequent overload is there, we use series motor, and otherwise we go for shunt motor. And one more thing that you can see, sometimes the load is of fluctuating nature. For example, you may have a load like this. And if this is the load, the torque, and this is the time. If this is the type of load, intermittent type of load, and we are using a shunt motor, in that case you will have a similar changes in the current also, like this. So you will have a highly fluctuating current, and that will cause a change in the, or fluctuation in the supply voltage. So in place of shunt motor, if I use series motor, in that case you will have a characteristic somewhat like this. It is less fluctuating, like this, because in this case the current is proportional to the square root of the torque. So on overload condition, the current will not become very high, so the current will be within safe limit, and less fluctuation in the supply current, less fluctuation in the supply voltage. So DC motor is recommended in those situations where we go for frequent overloads, and in those situations where the load is highly fluctuating, the use of series motor is recommended. So this is all about the characteristics of the DC motors. This is all basically a review of what you have studied in your previous course. Now in the next lecture we shall discuss the starting of DC motor, why it is necessary to use some starter, and for both series motor and shunt motor. So what is the remedy, and how you can limit the starting current to a safe value. So these things we shall discuss in the next lecture. Thank you for today.